Welcome back to calculus. So far we have seen how to find global max and minima when you do have a closed bounded interval and a continuous function. Then we just use the extreme value theorem. That's a really nice case. That is like the best when everything that you want to happen happens. And it's just wonderful. But not everything is like that, right? Sometimes you find yourself in more difficult situations. In particular, a lot of times you might have a continuous function, sure, but maybe the interval you're trying to optimize on is not closed and bounded. Like maybe you have all possible inputs are like the positive numbers. So you're dealing with some geometry problem and you want to like maximize the area of a circle or something. And the radius can be any positive number. So any r greater than 0. That's not a closed bounded interval. And we still want to be able to talk about things in that situation. So I did try to draw you some pictures a couple videos back that were showing that in general this is a tough thing to like. You might not even have a max or min all the time. But there is one special case that comes up a lot where even though we don't have a closed bounded interval and a continuous function, we can still say some stuff. And I don't really know the name of this theorem, so I just named it the useful theorem because it is incredibly useful and we want to cite it all the time. So it's good to give it a specific name. But it says this. It says essentially, if you only have one critical point, then you're kind of good to go. So we have a function and we're looking for the global max and min on some interval. And the theorem says if you only have one critical point and you know the local behavior, so you know if that's a local max or a local min, then the function, that point must also give a global max or min. So if you have a local max, it's actually a global max. And if you have a local min, it's actually a global min. Now, the function's only going to have one critical point, right? So this isn't going to give you both the max and the min, because if you only have one critical point, you're not going to have both. You're only going to have one. But a lot of times if you're optimizing, you're looking for like the maximum profit. You don't need to know what gives you the minimum profit, right? Or if you're trying to like optimize your path and take the minimal amount of steps, you don't need to know how to take the most steps. So oftentimes in applications, this is good enough. And this theorem is really, really useful in applications. Okay, so why would this be true? So I'm not going to give you a formal proof for this. It's a little bit too complicated for us, but I am going to try to explain it. So basically, if you have only one critical point, let's say you have a critical point, something like this. It doesn't have to be rounded off. It could be like this, or it could be a jump discontinuity, something like that. But you have some picture like this, and you've got a local maximum. So in all three of these pictures, there's a local max. And basically, that has to be the global max because the function cannot turn around. So if I think about this picture on the left, in order to go back up and get a global max, the function would have to like turn around and go back up, but then there would be this extra critical point there, right? And even if the function's all jagged or something, somehow it has to turn around, and that point would be a local minimum. And even if you had a jump discontinuity, maybe you've got something like this, that counts as a critical point as well, because if a function's not continuous, then it's not differentiable there, and that makes that point a critical point. So there's really no way the function can turn around, and if you just have, unless you have other critical points. So in cases where you have like multiple maxes and mins, you might have something like this. And then you can have this be your maximum, even though you've got these other local maxes here, right? But that's because the function could turn around in between. But with only a single critical point, there's no turning around, so that just can't happen. All right, so how we use this is we use this to find the global extrema of a function that is not on a closed bounded interval. And again, like I said, it's only going to find the max or the min, not both. But, you know, it's better than nothing. It's way better than nothing. So let's see a couple examples. I want to find the global extrema, if they exist. Let's just say global max and min for this function. Let's say we have f of x equals x plus 1 over x. Let's say for x greater than 0. Very common situation in real world problems. You just need your inputs to be positive. Maybe they're talking about length or something, or area. Okay, so note that's like saying that my interval I is the interval from 0 to infinity. So this is parentheses open on the left, and it has an infinity in it. So this is definitely not closed, and it's not bounded. Bad interval for optimization in general. But it doesn't mean there's nothing we can say about it. Our function, I should mention, is continuous. So at least we have that going for us. There is a discontinuity at 0, but that's not part of the domain we're looking at. So our function is continuous on this particular interval. Okay, so what are we going to do? Well, the useful theorem says we need to see if we have any local maxes or mins. Okay, so first I'm going to find the local extrema. And I'm going to hope that because I'm making a video to demonstrate the usefulness of the useful theorem, that this only has a single critical point. So we need to find f prime of x and set it equal to 0. That's how you find critical points. This function is just power, so we're not going to have any like sharp corners or anything. So we only need to see where the derivative is 0. It'll be defined everywhere. So let's see, we got 1 plus, and then remember this is really x to the negative 1 power. So when we take the derivative, we get negative 1 x to the negative 2. And that is the same as 1 minus 1 over x squared. Okay, so then we set this equal to 0. And that tells me that 1 equals 1 over x squared, just adding the 1 over x squared to the other side. And then I'm going to multiply that x squared to the left. So I get x squared equals 1. And that tells me that x equals negative 1 or x equals positive 1. Okay, so I've only got 2 critical points for my function. Wonderful, right? Well, no, the useful theorem says I'm only supposed to have 1. But remember, I'm only looking at x greater than 0, which is this interval, so I don't care about x equals negative 1. This is not an I, so we don't care about it. We only care about what's going on in the interval. So let me keep my function here. X equals 1 is the only critical point in I. The only critical point of f of x in our interval I. And that is great because that says we can apply the useful theorem. So now we have to decide if this is a local max or min, and then the useful theorem will tell us whatever it is, that's also the global one. So how do we know if a critical point is a local max or min? Well, we know how to do that, right? We can do the first derivative test, or we can do the second derivative test. And in this case, the second derivative looks really easy. So I'm going to go ahead and take the second derivative. So remember, f prime of x is this guy up here. So if I take f double prime of x, the 1 just becomes a 0. It's a constant when I take the derivative. And then I have that negative 1. The negative 2 is going to come down in front, and I get x to the negative 3 power. The 2 minuses make a plus, so I really get 2 over x cubed. Okay? And specifically, f double prime at my critical point is equal to 2. 2 over 1 cubed, but we'll just say 2. So that is positive. And what does it say if the second derivative is positive? So that means that my function is concave up. So the graph has a local minimum, or the function has a local minimum. Okay? So by the second derivative test, or let's say the second derivative test tells me that f has a local minimum, right? The function's concave up. So it looks like that-ish. Local min at x equals 1. And then the useful theorem says, and this is because I only have one critical point and that critical point is a local min, it tells me that f has a global min. At x equals 1. Okay, so we are halfway done. We know about the minima. What about the max? I mean, I guess theoretically it could, I don't know, maybe the function's got a max or something that we didn't find. So it's tricky. We can't just apply some theorem, but what we can do is we can look at limits. So for the max, let's note that if I take the limit as x goes to infinity, that is one of the endpoints of my interval, right? I go as far out to the right as I want, and that's part of my interval. So this is the limit as x goes to infinity of x plus 1 over x. That was my original function. So the 1 over x part is going to go to 0, but the x part, this part right here, that goes to infinity. So the limit is plus infinity. Now, if your function has a limit of infinity, it just keeps getting bigger and bigger as you go to the right? Maybe there's some wiggles or something before, but eventually your function just gets really, really big. So there is no, that is enough to tell you there is no global max. Because if there was a global max, eventually you could go far enough to the right to get even bigger than that. So now we know there is a global min, it occurs at x equals 1, and there is a global max. Now I didn't find what the maximum actually is, unfortunately. I'm not done yet. So I know where the global minimum occurs, but I haven't actually found the minimum. So the global minimum is, how do you find the minimum? The global min. Well, it turns out that part's pretty easy. We know where it occurs, so we just plug that into the function. So it's f of the place where the minimum occurs. So that's 1 plus 1 over 1. Remember, my function is x plus 1 over x. So that's 2. Okay, so the global minimum is 2, and it occurs at x equals 1. F of 1 equals 2. Okay, so we can look at this. I thought I'd plot it on Desmos for it, not that one. Desmos. Aha, so I plotted x plus 1 over x just for x greater than 0, and we can see it's got this minimum right here at 1 comma 2. And actually, I could have taken the limit as x goes to 0 from the right as well, and I'd go the function going up and up and up to infinity, and no matter how much I zoom out, that function is just getting bigger and bigger. There's definitely no global minimum. Or sorry, there is a global, there is no global maximum, so I'm not going to waste time trying to find it. Okay, so let's try another one where maybe we don't have this infinity stuff going on. What if we just have a function on an open interval, but it doesn't go off to infinity? So again, I want to find the global extrema, if they exist. For a function, and we'll pick a simple function so we can just see how this works. I mean, the useful theorem doesn't apply to weird functions with lots of critical points, right? So let's just say we have f of x equals negative x squared plus 12x. Okay, you might recognize this as a downward opening parabola. So you can tell just by knowing about parabolas that it's going to have a maximum, right? That's how parabolas work. And let's say we want to do this on the interval I equals the interval from 0 to 10 with parentheses on both sides, so we don't include the 0 and we don't include the 10. Okay, now in this case, I'm just going to graph it to kind of get an idea of what this looks like. So let's say 10 is somewhere over here. And, well, I actually know this function, right? Negative x squared plus 12x. I know that's 0 when x equals 0. Let me factor it in case you can't see this. So I can factor out an x, and then I get x times 12 minus x. So this is going to have zeros at 0. I'm going to put an open circle there because 0 is not actually part of the domain of the function, right? We've got a parenthesis at 0. So we're going to have an open circle there. And then it's going to have a 0 at 12 over here. But the function doesn't go down that far. So it's actually going to look something like this. And then it would keep going down and hit 0 there. But we're not including that as part of our domain. Oops. Something like that. So we're going to have these open circles on the left and right. So I would argue that just from this picture, we can tell that there's no global minimum. On I. You could also argue that f of 0 equals 0, and everywhere to the right, the function is bigger than 0, so 0 should be the minimum, but it never actually hits that value because 0 is not part of our interval, so there's not going to be a global minimum. We can get, the function values can get closer and closer to 0, but never actually get there. But what about the global maximum? So if you know the vertex formula, you can deal with parabolas without calculus, but calculus actually makes it really simple. So I'm just going to take f prime of x. Remember, my f of x formula is up here. So we'll take f prime, that is negative 2x plus 12. We're going to set that equal to 0. And that tells me that x equals 6 is the only critical point. Guess what? That point happens to be in the interval I. So we just need to classify it. So let's classify it. I guess I'll use the second derivative test again because that's really simple. F double prime of x equals negative 2. So specifically, f double prime at the critical point is negative 2. That is negative. It even has negative in the name. So we have a local max. The graph is concave down, so at the critical point it must be a local max. So we conclude first, f has a local max at x equals 2. That's by the second derivative test. And then once you know we have only one critical point, and that is a local max, the useful theorem says that is a global max. So we have a global max at x equals 2, and it's global by the useful theorem. So there are actually lots of really good theorems in math that take local information and turn them into global information. There's even a thing, they're called local to global theorems. You can look it up on Wikipedia or something if you don't believe me. Or if you do believe me, that'd be a better reason to look it up. So you can look up local to global theorems. And a lot of them are about patching together a bunch of little local information to get a global picture of what a function looks like. But this definitely counts as a local to global theorem. You know something about the local behavior, and then you use other things about it, like no other critical points, to show what the global behavior is. Okay? And I guess we should actually figure out what the global max is. So what was my function again? It was x squared minus 12x. So we just plug in. The maximum is f of 2. So that's going to be 2 squared minus 12 times 2. No. Plus. Oh, what happened? What happened? Oops, sorry. Sorry. Negative x squared plus 12x. Okay. So negative 2 squared plus 12 times 2. So that is 24 minus 4 equals 20. So the maximum is 20, and it occurs at x equals 2. Okay? So yeah, useful theorem. I wouldn't have given it the name if it wasn't actually useful. We will see this a lot as we're doing optimization. Please make sure you actually cite it when you use it, though. It's a good one to recognize that you're actually using it and that you're being careful. So with that, I think we'll be done, and I'll see you next time.